So we'll continue our discussion on next generation lithography. Last time we discussed about the extreme UV lithography, which can be taken as an extension of UV lithography, and electron beam lithography and ion beam lithography, which basically started from scanning electron microscopes, and now we have a use of electron microscopes where we can use the electron beam to write features, and another equipment called focused ion beam, with which we can use the ions to write features, right? So they both have been extensions of microscopes, electron microscopes. So in case of focused ion beam, we call that machine FIB, focused ion beam. Today we'll look at scanning probe lithography, or scanning probe basically is the idea that we have these very tiny small tips, which they're very thin, nanometer scale, so we can use them to write very small features. But this is more of a physical feature where we are writing directly. So to get into that, let's take a look at the principle of atomic force microscope, because understanding atomic force microscope helps us get a feel of how small are those things and how do we interact with those things. One of the students, I think Myra has a KPR presentation on that also, which is posted on the channel. So that gives you a little bit more detail on that. So we have a cantilever, which is this projected like a jumping board in a swimming pool, which is, so this cantilever is held from one side and free from the other side. And this cantilever has this a small tip, which is created by MEMS fabrication. So what we do is we bring that tip close to the surface, to the sample, and we scratch it, right? So we move it on the surface. By doing that, we can see the topographic height of the surface. So we can measure topographical features on the surface. Now, it's very thin, and it's coming in contact with few atoms on the surface. So there are forces between the tip, which is on the cantilever, and the sample. So we can measure those forces by bringing this tip in close proximity and pulling that away. So that is one thing where we can measure the type of the surface material. And when we drag it, when we move it, then we can measure the nanoscale features on the surface. So atomic force microscope is a derivative of other things where it started scanning tunneling microscope. So there, where we were using tunneling current measurement to see that how there was conductivity between the tip and the surface. For that, the surface has to be conductive. But for atomic force microscope, since it's a physical scratching kind, the surface doesn't have to be electrically conductive, which means that we can do proteins or biological samples as well. So this picture is showing proteins on the surface. So tip is coming in contact, and then we are pulling it away. So we are measuring the forces that would be there in that protein, right? So unfolding, folding, so these kind of things.
Sir?
Yeah, go ahead.
Sir, I also ask question with her, sir, in YouTube channel, sir. Can we scan in liquid, sir? Atomic force microscope, sir.
Can we do it? Can we do what?
Can we scan in liquid, sir?
Yeah. So AFM can be used in liquid, but you have to understand the forces. There'll be extra forces when we are dealing with liquid surfaces as well. And that's, today we were looking at that as well. How can we use AFM to use liquid or image things that are in liquid? This picture is showing exactly that, because the biological molecules or biological entities are wet. So they have lots of ions, and of course, water molecules in there. Now, this cantilever bending, right, up or down, when you're bringing it, the whole platform close or taking away, we can measure the bending many ways. We can have current, of course, from the tip and the surface, which is STM, and we can measure we can infer from put a fiber optic and see light change. We can put piezo-resistive materials to see the bending. This picture is showing a very simple setup, which is the optical reflection, right? So at the back of the cantilever is a shiny part. So we have a laser pointing there, and laser is being reflected from the back. Now that reflected laser is measured by photodetectors. This example is showing 4 photodetectors. And I put these red arrows that if it would move up, down, right, left, if it twists, if it moves up, down, you can see from 4 photodetectors that the reflected laser point will be moving. And that's what we would take into a computer and use that to create an image. So there are there are 3 basic parts of an AFM. Of course, a tip on the cantilever, which is going to come in contact, then piezoelectric scanner. So this is the stage on which we have put the sample. So we have to move stage in a very precise way in X, Y, Z. X, Y is when we are scanning, Z is to bring it in contact, right? So those piezoelectric elements can give us very precise nanoscale movements. Now, once in contact and once the imaging is happening, then we would either move the stage and tip stays, or we move the tip, whichever is the case. That's a different mechanism adopted in different applications of AFM. Now, when the cantilever is deflecting because of the surface topographical features, we are measuring the deflection from the reflected laser spot through photodiodes. So a fundamental would be 4 photodiodes, but can have a bigger array of photodiodes also. Now that the moment in XY and the deflected, so we take it in a computer, and that's what we use to translate this information to create a topographical image. We'll look at many of these images today. So the basic function of AFM is to look at topography of surfaces using the attractive or repulsive forces between the tip and the sample. So it's a force sensor, and it's a force sensor and a force actuator both as well, because the very sharp tip is coming in contact between the tip and few atoms of the sample. So we are measuring atomic level forces there. So those the forces between the atom and the tip, they start playing a role as even at 100 nanometer, when you're so close, depending on the surface. So these forces start acting up from 0.1 nanometer to 100 nanometer, between that range. And now these forces, can be classified as attractive and repulsive forces. So think about, you're bringing tip. So there are 2 types of forces, those that may be attracting it close to the surface, and those they may be repulsive, trying to push it away. Now we are measuring those forces, right? Because we have control over the cantilever or the tip. Now, the attractive forces, generally there are van der Waals forces, there are electrostatic forces, and there may be chemical forces depending on what material is there on the surface. And there are many models. We are still learning a lot about those forces at nanoscale. And now there are repulsive forces as well, which may be the actual surface hard material-based repulsion. There's poly exclusion interaction. There's electron-electron Coulomb repulsion. So generally these 2 forces are there. The repulsive forces are short range because they are atomic scale forces, and they exponentially decay when the tip goes away from the surface. So I just wrote down a few forces that come into contact when we are dealing with an AFM. Now, we use it for imaging, but now if you want to make features on the surface, so this would be something like, I put this picture in the top left corner, plowing a field, right? So the bull, pair of bull has a bull cart, and the cart has this thing which goes in the ground to plow the field. We have machinery and tractors now to do that. So, but here is a similar concept. The tip will come in the close in contact with the surface, and this would be what would remove the material or modify the material on the surface. And hence we can write what we want to write. So those small trenches or the interaction of the tip can result into, we can write molecules. So if the tip is dipped into some solution and brought there, we can put those thin lines like these old pens. You know, they had the pen with the feather of bird. You would dip it in ink and they would write. They show it in old movies. So, but here we have very precise control of where we are writing and what we are writing. That's written here, molecular writing. We can have magnetic change on the atoms on the surface. So in the framework, whatever we are doing, we have to know what is the material and what is the tip properties to do that. We can scratch mechanically, like it's given in the right lower image, or we can chemically modify the surface, right? So you have one reactant on the surface coating, one reactant on the tip, they come in contact, the chemical reaction happens, and that changes things at that nanoscale. So the advantage is clear. We can write very small things, very small resolution. We can write things very close to each other, which means the pitch, right? So we have smaller pitch. And we have very reliable writing because we know exactly where we are writing. But the biggest problem is throughput, how fast we can write. And there are lots of things that go into defining throughput. We'll look at that. The first example of this molecular writing has been patented, and they have made a company of this. It's called dip pen nanolithography. So they call it DPN.
Sir?
Yep.
Sir, can we see a individual? It means can we see an individual atom with sir AFM as well, sir?
Yeah. So when we are writing, we are not seeing, but we know the surface. Once we have written, then you can use another system, another tip. You don't have to change, just the tip.
Like,
and then we can use the tip to look at where the features have been written.
Like in STM, sir, we apply very low temperature to move atoms from one place to another place, sir.
So that was one application, right? So STM doesn't have to be done at low temperature, but that was one application from IBM where they did that 20 years ago to ultra cool the substrate, so the atoms could have low thermal budget, so you could easily have more magnetic forces become more prominent to move those around. So, but there are many applications on that. So here we are focusing on what kind of lithography can we do? Next generation lithography. Emma needs to be muted. All right, I'm trying to do that. All right. So here in this case, dip pen DPN, dip pen nanolithography has become it's a product there. So they are selling these systems. What the idea is that we have to use an ink. What you call ink is molecules dissolved in solution. So when we write down the molecules and the substrate, they have affinity. So the idea is to get self-assembled monolayer out of that. So once the molecule gets to the surface, meniscus would result, the surface tension would result into the liquid spreading and resulting in those molecules, because of the functional groups that they are there, would result into orientation of those molecules. Of course, a lot of it is cartoon, but we have a good control over the engineered molecule that we're using to create SAMs. So, so this has been around for many years. There's a recent review paper on that from Dr. Chad Merkin's lab. So Chad Merkin at Northwestern University here in USA is one of the earlier person who has been doing that. So here they are just recapping some of the things they have done. So now there are a lot more forces go into it. When you were talking about liquid, so yes, so liquid has this surface tension, you have this meniscus formed, and molecules need to diffuse down to the surface. And that diffusion, ultimately, once they get to the surface, then their self-assembly comes into play and they form features like they're shown in the right-hand top picture. So you see the scale bar is 100 nanometer, 1000 nanometers there. So which means that now they have they've done characterization of how they get there and using different time of contact, 6 second, 9 second. So the longer you do, the bigger dot you would get. And then they have, so they call it dwell time, right? So how long you leave it there, and that will result into different size that we can get. So, but the earlier version, so how do we get the ink there? So there have been many studies on that also from their group and other people, where people have made kind of small chambers using MEMS techniques to etch stuff. So now, and then they put ink. What you call ink is the liquid with molecules that need to be written in a chamber, and they flow, and on the tip surface, then they can write. And this ink can be, it's unlimited possibilities what you can write. You can write, you can dissolve organic molecules, write them. You can get nanoparticles in solution, you can write them. You can get polymers, DNA, a whole bunch of things that can be written on the surface. And when we talk about biomolecules, then of course, the next thing would be to use them as a sensor, right? So use them as the selective agents that can bind to whatever we are looking for. Issues, again, throughput. How fast can we write, right? So that throughput results into cost. Throughput results into how much are we willing to pay to get that kind of things. So when you go into characterization, so if you move it too fast, the line thickness would be thin, right? So this plot given on the right-hand side, you have to know the tip speed is inverse, which means if you go to a bigger number, you are talking about smaller speed, right? So smaller speed gives you bigger thickness. Higher speed can give you smaller line thickness. Question, Ahmed, go.
So you said in the beginning that in the last you said that we need sort of like a greater true speed and a smaller, like it should be on the far right. I can't remember what it was. The true speed, I think.
Talking about Tennant's law that we were
Yes.
talking last time.
Yes.
That was
Yes.
about resolution and throughput. So if you make something, now this is, so that was the motivation of why we want to do next generation lithography.
Yes,
right?
but according to the graph, it was going diagonally, linearly upwards. It was not
So-
going this direction. Therefore, we need to be at the midpoint of that or something.
Right.
At the place
So
where they
now we
cross.
wanted, if you remember, we wanted to be the right lower corner where we wanted to have smaller resolution and high throughput,
Yes.
right? So here, what we are talking about is a different thing, but that relationship still holds that if you want to write smaller things, right, you have to have high throughput. But here we are talking, we want to write smaller, the characterization of how fast should we move our tip.
Okay.
Right? So if you move too fast, you can have smaller line. If you move slower, you can have, your line will be thicker. But now if this speed or this throughput good enough to create billions of transistors, that would be the question. Because that plot was talking about how many devices you can put down in unit time.
Okay.
But yes, you're right. That's why this is being done, where we want to have smaller resolution and high throughput. That's the whole
Yes.
idea of next generation lithography. That
Yes, sir,
that
but,
is the wish list.
but according to your graph set, they both would increase linearly. So you were saying we need the
That
bottom
was
right
not
to,
linear. That was not a linear plot. That was a power plot. That the both x and y were logarithmic there.
allow it. So
It
we
was
need
not a
below
linear plot.
line, we prefer a below line or do we prefer above line? So
We
below
want to
line
be on
or
the we want to be in the right lower corner on the Tennant's law plot.
right lower corner, sir. Okay.
Right lower corner.
Okay. Well,
But
like below the line,
you
below
have to
line.
look, you have to go through that lecture from last lecture. You will understand what we were talking there.
Okay.
Right?
Okay.
Yeah.
Thank you, sir.
So it has to be on Tennant's law plot. We want to be on the right side lower corner. Low, smaller resolution, high throughput. Right? So to achieve that, we are looking at next generation lithography techniques. Right? So another thing that can be done is we can heat up the tip and we can coat ink that becomes active when we heat it up. So we can then keep on going and only turn it on where we want to write and turn off where we don't want to write. So it can scratch the whole surface. Now in this case, we are not blowing, we are just scratching the surface gently. And wherever we want to write something, the ink is coated on the tip. We heat it up, the ink starts flowing, starts writing. Where we don't want to write, we turn off the heating and it does not write in that. So there are many different ways they have been playing with that. Now, to have high throughput, there are ways how this has been tried where they have made big arrays, many tips together. Like on left one is showing 10 pen array. So now they're coming with 10 tips at a time, writing, going up, moving and writing these things in a parallel fashion. So then the idea is that we can parallelize and write same pattern in parallel at different places. Right? They have done 5 by 26 pens kind of thing. So there's a company who is continuously coming up with newer and newer products. So they made a company called Nanoink, where they are using this DPN approach to parallelize the write-up. So this is another example. So this is an AFM image of the writing platform, which has 100 nanometer tips, and each tip is separated by 400 nanometer. So now this thing, it's showing upside down. And you will bring this and write on the substrate and stamp and keep on going. So this is the image taken from this one of the block, which is showing those 100 nanometer wide ink spot was written 400 nanometer apart. Right? So this is huge parallelization to get high throughput. Another way, oxidation. So we talked about oxidation, right? So oxidation is doing oxidation of any material can result into material changing into its oxide form, right? Silicon turns into silicon dioxide. We can do that by localized voltage application in some material as well. So that high electric field would oxidize that material there, right? For example, silicon itself. And that would result into, now, if you look at this image, so this is about 1.6 micrometer and 1.6 micrometer on the other side. The color code from green to blue is showing nanometers. So the green part, if you look closely, green part here is about, this is 1 nanometer. And this blue, really blue, starts from 2.5 to 4 nanometer. So these are the height of that oxidized area where the tip came, and with the application of voltage, it oxidized silicon in that, just that area where now you can write the feature with the tip, right? We can anodize material. So the idea is that with high electric field, you change the material property, and that is a way of writing the feature down on the substrate. All right. Yeah, Emma, question. Emma, did you raise hand, or you never brought your hand down? All right.
Sorry.
All right, it's okay, it's okay. So the AFM lithography we have been used with polymers, right? So where we put down polymeric films with sharp tips. In this case, you can scratch or you can apply this line in a polymer and then etch the whole line. So this, wherever we did the writing, becomes a kind of a mask, which means the etching will not occur where you have written, but etching has happened everywhere else. And that gives you this kind of feature, which is about, I don't know, 10 nanometers thick. If you take this, the scale bar, and you transfer 200 nanometers to that top of that feature, it's few nanometers, pretty thin at the very top. On the right-hand side again, 120 nanometer scale bar, if you transfer it at the top, it's probably 10, 15 nanometers. So that's the sub 100 nanometer resolution that we are getting. And polymers again are soft and pliable. So even the tip that we are using would not have too much drag because the polymer is soft. And so because tips, they get bad. When you do writing, there's after some time the tips become dull. They would stop writing those thin features. So you have to change the tip, get a new one. So this tip sharpness degrades with exposure, dose, how much voltage you are applying, how long you are applying, and what kind of resist you are using on the surface. So the mechanical drag, or mechanical kind of wear and tear would bring the sharpness, reduce the sharpness, would become dull. All right, so now something that Emma was referring to, STM, which was done in 1993, where they used scanning tunneling microscope probe to pick individual atom and place them in certain order. So this was, they made a walking boy video, they made this one, they wrote IBM, so lots of cool things they did. But it cannot be called lithography, but it shows you the strength of and further work that can be done with tips to write smaller features, and hopefully have small features, high resolution, but the goal is to increase throughput, right? So this is about scanning probe lithography, scanning probe, the tip with which you can write things. Now, over years, we went into another direction using these tricks of microelectronics lithography, an area what we call soft lithography. Now, I'm not calling it nanolithography, I'm calling it soft lithography. The idea is making features in polymers, making features in soft, pliable materials. PDMS, if you have not heard the name PDMS, if you look into lab-on-chip devices, PDMS is kind of a workhorse. PDMS is the material of choice because it's a soft polymer. It doesn't have chemical problems, like it's not carcinogenic, it's not corrosive, it's easy to deal on benchtop. So PDMS has become it's polydimethylsiloxane, something like that. We take the chemical, shorten the chemical name. So what we do is we use PDMS to make features in it, to make, like we looked at that PCR microchip, right? So that plastic thing was put there, and it has holes and channels and mixers and valves. They all are made in PDMS for the most part. But we have to make those features in that polymer first. So that's the area which has become to be called as soft lithography. So just like we do in devices, we make circuit, we will put it on a mask, and then we do projection lithography and we make our chip surfaces. Here, what we would do all those things, but we are not making circuits. Now we are making channels and pathways for solution. And once we put it on the wafer, we make these 3D groovy things design and use that as a stem. So we put the wafer down and we pour our plastic on top and we let it dry. Once it dries, we take it apart and that design is now transferred in the in your PDMS, in your polymer. So here what is showing is the stamp would be the wafer. And with that, you can either make directly your polymer device that you use, or you can make a master out of this. So which would be now used to make more devices out of that. Now you can take the master and you can coat it with molecules and bring on a chip surface and transfer those molecules. Just a couple of examples before we get into more detailed types. So the idea is contact printing. Contact printing, there are 5 types of contact printing. And this is what is done in laser printers as well, right? Laser printer has a drum. So when the paper, it gets the ink coated on this, when the paper comes through it, the ink gets transferred. Heat makes the ink stick and you get a printout which has the image or whatever needs to be printed. This is the idea. Now lithography is the number 3, what it shows here is the chemical patterning of flat surface, right? So what basically we are done in photolithography also, right? So we are patterning a flat surface and we are using photoresist. But here we are doing slightly differently. What we are doing is we're doing these type of things. Now we don't really differentiate between that, but there are 5, 6 types of soft lithography things when they are being developed. And I will not go into all of them, but the idea is that depending on what was the master, what was the transfer procedure, or how the transfer was occurring, they were differentiated differently. But the basic idea stays the same, that we are using a hard substrate, silicon wafer, to make features on it. Then we are pouring our polymer. The polymer may be the actual device that we want to make, or we pour the polymer and make a master out of it. So instead of every time going to the silicon wafer, now we have a master which is cured, made hard, and we use that to create our devices. All right, so soft lithography, 3 basic things that go into that. Self-assembly, we already know. Spontaneous aggregation or organization of molecules, right? Where we have already engineered the functional groups in there. So we know that if you make something of gold, if your surface is made of gold, we use sulfahedral SH group. So we know SH binds to gold. If we have a functional group that's hydrophobic, so we are doing self-assembly in water, which means hydrophobic part will try to go down and hydrophilic parts will try to stay towards the water side. Hence, they will self-assemble the molecule. Now, self-assembled monolayer SAM is something which we make when we do self-assembly. So in a SAM, the molecule will have 3 components. Of course, the head group, which we want to be available to the whatever function we have to do afterwards. There'll be this chain of carbon, which is shown as a kind of a squarey kind of thing in the middle. And Y is the functional group or the anchoring group, which goes down towards the chip surface or the PDMS surface, right? So these 3 parts will give, so this carbon chain would be, we are using 12 carbon, 15 carbon, as long as you want to make So that will, once they get assembled, you say you have a SAM. And then it may be for biosensing, it may be for just for coating, it may be because you don't want two surfaces to stick together. So we do all kind of SAMs to achieve results. So SAM, the idea is it's a few atom thick, right? 1 or 2 molecule thick layer that we want to create on the surface. And that plays a big role in soft lithography, because when you put, for example, you put polymer on a silicon surface and you have the features, sometimes it's hard to tear it apart. It gets stuck. So before you put your polymer, we put SAM of molecules which would not let the polymer adhere very tightly. So it's easy to peel it off. When you're doing your lab on chip, so you have the whole channels made in your polymer. Now you have to put it on a flat substrate. So in that case, you want it to really stick to the surface. So in that case, also we make SAM of molecules that we want them to really make it stick. Now, when you have a reaction chamber where you want to do some reaction between your probe molecules and your target molecules. So sometimes you want to make SAM there also, right? So there is a whole bunch of things why we make self-assembled monolayers. PDMS is an elastomer. It's a long silicon oxide chain backbone molecule, right? And it has a glassification temperature. That's temperature that once you heat it above that, it solidifies. It becomes like glass. That gives you transparent way. And of course, there are lots of chemistries that you can do on the PDMS surface. It's hydrophobic, so you have to make it hydrophilic. It gives you transparent view. It's not reactive. It's easy to functionalize. So there are lots of things that have made PDMS to be the material of choice to do lab on chip or for soft lithography. All right, let's look at an example of soft lithography. So you have the silicon wafer, you do your microfabrication, we did some mask, we did the optical lithography, we made a feature, right? So H mu is, let me clean the screen. So H mu is showing that you did optical lithography, right? UV light. Now, once you get that, you have done maybe etching or whatever you have done. Now you have made this feature on the surface of your chip, which is shown in this maroon color, right? Now we put PDMS on top, we let it settle, we put it in vacuum chambers, so we want to get rid of all the bubbles from that polymer. We heat it, but not above glassification level. We don't want it to become really solid. We want it to become semi-solid. But during that time, the polymer would take the shape of whatever feature was there. And now you peel it off and you have your PDMS stem. So in this case, we may be using it to transfer molecules, not maybe transferring molecules at a predetermined position on the raised parts. Or maybe we use it as a master, and then in that case, we would now flip the PDMS, we would make it solidify, and we'd use that to pour material on top and peel off, right? So it depends on whatever application we are doing. Now, if we need to make nanoscale features, then our lithography will have to be done in a way that we get our nanoscale features, right? So in this case, then probably we would use next generation lithography to do this process, right? So which means we want to make smaller features, depends on our application. But then we have to also see that the pattern has to be big enough that it can be transferred into PDMS. So there are many different characterizations that have been done. We can look at literature, we can know that what kind of feature or dimensions that we can make that can easily get transferred into our PDMS. We also do sometimes there are some resists which are very thick. So we put those resists down, there's an SU8 family. They're called SU8 resists. SU8 2000, SU8 3000. They're a whole class of those resists. So those resists make very thick films. We do the lithography, and that resist gives us those higher height. So regular photoresist is very thin. If you want to make thicker structures, so you can make thicker features in your PDMS, so we use specialized resist in that case. Now, these channels, whatever you want to make, it would be the design that would be used in the first step, right? So lithography is what will define the ultimate thing that will be made in the PDMS. So here in the last bullet point, it says master is treated with the release agent. So sometimes they become too stick. So we make a SAM of some molecules, which are release agent. So afterward, when we are peeling off semi-solid PDMS, it doesn't adhere too tightly there. All right? So far with me? Are you guys with me? Half of the class has no video feed, so I have no idea if you are with me. Those who have the video on, thank you. All right, so micro contact printing. So now this has the bottom up, which is optical lithography, and sorry, the bottom up fabrication is where we deal with molecules. We design specialized molecules. Top down is optical lithography. So here it's using top down fabrication and bottom up fabrication both. So the idea is that if you look at PDMS, the raised part is where the relief structure is. The molecule which are there on the raised part, once they will come in contact with silicon, the raised part will leave their molecule. So in this case, it's an alkane thiol. Thiol is SH group, sulfide group. So alkane is long carbon chain. So these are molecules which it will leave the molecule there, right? So we stamped it. In next step, we may want to use that alkane thiol to put DNA molecules down, maybe make a assembly of probe molecules to look for some target molecule, right? In our lab, we have done these kind of probe molecules to look for cancer genes, so lung cancer gene, for example. We have done some work to use these surface-bound antibodies to capture overexpressed biomarkers, cancer biomarkers. So what you do, you have made a big patch of alkane thiols, and then you are using bottom-up self-assembly of DNA molecules or maybe protein molecules to put on the surface, and then whatever things come after that. And this example from this paper for Journal of American Chemical Society, what they're doing is in that area of sensing, when the capture will occur, they have made electrodes to the outer world, which means you can measure with your voltmeters, very sensitive voltmeters, not regular desktop voltmeters, to measure change in resistance, maybe measure change in capacitance when their target molecule binds there, right? So it's one application of micro contact printing. All right, so micro transfer molding is micro transfer molding. So in this case, what they're doing is, so they are made wells in PDMS which have been filled with pre-polymer, and they bring it down, and they're transferring that what's shown as golden molecule, and they're making these patches of golden molecules on the surface, and then they are curing it. Curing is heating it up to make it hard. That's another kind of soft lithography. There is a whole bunch of things. This micro transfer molding, mimic, replica molding. So they are shown side by side. The bottom line in all those cases is we are making features using microfabrication, etching, lithography, and then we are using them to either fill the small trenches, transferring it, or like in mimic, we make the capillaries, and then we introduce the molecules at the side and capillary action will fill it up. Or on the right side, replica molding, what we are doing is we are using that PDMS to create an opposite features on top of that. So in this case, PDMS is being used as the master for the die. If any of you have ever seen the what they say foundry where they make stainless steel things, or maybe I don't know, there are lots of factories where they have small molds of things. They put the molten metal in there, it takes a shape. If you have some concept of that, these are just derivative of those kind of things. Now with replica molding, we can make very small features, because what we are doing is we are using next generation lithography. We can make very, very small features in PDMS, and those can be transferred in other materials. So these are showing the gold structures made on a master, and then which is shown in A, and those A and B, and those have been used to now transfer into many, many more devices with similar dimensions, right? So think about it. This is, instead of doing lithography to make small things, you can make one master with next generation lithography and keep on stamping, not stamping, keep on pouring things and peeling off, and you can keep on transferring those patterns into other materials, right? All right, so let's look at few more examples and then we'll stop. So this showing these lab on chip devices are not one single layer. There are many multiple layers. These multiple layers may be to do kind of a running different liquids and bringing them together in some chamber, right? What we would do in a lab, right? So you want to keep things separate. They may be used to doing the valve effect. So which would mean if you pressurize the top one, it can pinch the lower channel. In this case, you are turning valve on and off. So there are many multi-layered approaches to create soft lithography, where we would start with one level and then we would create another level on top of that. So this is showing the pressure actuated valve, where you would push the liquid in the top layer and that would pinch the liquid in the lower layer. Another multi-layered lab on chip application. This is another application where you have different layers. Now it's color coded here to show there are control valves. There's a flow layer where the liquids are flowing. There's latching. I don't know what they're using the word latching in this case. And then there are reservoirs which are just keeping the solution in there. So depending on your application, we can actuate from outside. And actuation would be, again, can be an electrical mechanism to actuate, where you pump some solution in or you stop some solution from going in. All right, so few applications. Now, PDMS has its own issues as well. It's a polymer. You harden it, becomes glassified. It becomes glass. It can, when it's, now, if it becomes hard, then it can become fractured if you put too much pressure. If it's soft, it can become, at some places, it can have effect of gravity. It can make the channels smaller. It can collapse. So these can result into the defects in the pattern. Adhesion can be issue. We always have issues of leakage of solutions because PDM is not adhering well to the substrate. These are small channels. They can be capillary forces which can push fluids in directions we don't want them to go. Since it's a moldy, what do you call it? It's a soft polymer. You cannot make high aspect features in it because they would sag. right? They can fall over, they can collapse. Low aspect can sag, which means that the feature cannot be clearly distinguishable. So you have to play with this, but there's lots of data on this to learn and not repeat the mistakes that other would have done. It's hydrophobic, which means the water doesn't stick to it. So which can be good thing, bad thing. But if you're flowing through, we need to make sure the surface is hydrophilic. So the solution cannot create bubbles in it, right? But it can withstand a lot of kind of flow. Many different kind of solutions can be used with it. But there are issues with PDMS as well. All right, so let's look at some more examples using the issues with PDMS. So what is showing the collapsing of PDMS structure, which can result into blocking of the channel, right? There can be features that can become recessed. So if two parts they fall on each other, they can remove the feature at all. You wouldn't see that. So there are, when we make the contact, we have to know exactly what force do we use. We cannot overdo that when we are doing the contact. So it's a very process which has to be done very carefully, right? Now, features may not get transferred. That's the lowest example. So there are ways how it's been done. So now this is showing comparison between two types of PDMS. One is CellGuard 184, and then they have come up with another variation of which is called HI 184, right? So what PDMS we use, we have to look at the data sheet and the existing literature to get a feel of that. Now, there are many different ways how this has been used. There is a group who makes lab-on-chip CDs. You know, CD compact disc, CD rotates. So they're using the centrifugal forces to mix chemicals. So the idea is, yeah, to do a testing, you put the chemical or the whatever solution on a CD chamber, put it in the CD player and let it run. Maybe 2 minutes, you take it out and all the reaction has been done. This is showing example of cell lysis. Cell lysis is breaking apart cell boundaries. So removing the cell boundary and having a mixture of whatever was there in a cell. So this is Dr. Mark Madhu is a fantastic guy from Irvine, UC Irvine, who is considered to be the early godfather of MEMS and bio-MEMS. I've met him a few times. So anyway, so this is some work from his lab. Questions?
So how